Hello and good morning, and welcome to the lecture number 4 of this video course on advanced hydrology. In the last class, we looked at the derivation of the Reynolds transport theorem. What I would like to do today is go over it again and look at some of the steps more closely, just in case some of you were not able to follow it. I am doing it because this is extremely important to understand various steps involved in the derivation and understand different terms in this Reynolds transport theorem. So, what I would like to do is come back to this board and define that the Reynolds transport theorem basically gives us this: the time rate of change of extensive property, all right, is equal to the sum of two components, that is component 1 and component 2 as shown here. What is component 1? Component 1 is nothing but the time rate of change of extensive property stored within the control volume, that is this is your component 1, and that is defined as the time rate of change of B stored within the control volume. And component 2 is the outflux of the extensive property flowing across the control surface, all right. That is to say, component 2 is the net outflux or net outflow of the extensive property across the control surface, all right. So, what we will do is we will just write these two quantities, and what we did is we defined the control volume using this schematic diagram, in which we defined regions 1, 2 and 3, where region 1 was the region at time t only, region 2 was the region the fluid occupies at time t and t plus delta t, and region 3 is the region the fluid occupies at time t plus delta t only. Then what we did is we took a very small elemental volume dV, this one, within the control volume, all right. And then what we did is we wrote the expression for the amount of extensive property within this dV, and then we said that to find the total we integrated over the whole area or whole volume. So, I will just jump to the next step. This is the expression we said, equation number 1, which comes out to be the extensive property stored within the control volume. Okay. Then we moved ahead and we said that we will write the expression of dB by dt, that is the left hand side of our Reynolds transport theorem, using the first principles, that is how we define the first derivative using our knowledge of calculus, in which we said that dB by dt is nothing but the under the limits of your extensive property at time t plus delta t minus extensive property at time t, all right. And using the definitions of our different regions, we have extensive property at time t plus delta t in regions 2 and 3, and the extensive properties at time t in regions 1 and 2, all right. So, we wrote this equation and then we did some slight rearrangement, all right, and then we will deal with the first term is this and the second term this, one by one. Okay. Moving then further, we try to write this first term as under the limits of 1 over delta t of your B2 at time t plus delta t minus B2 at t, all right. This we say is nothing but the first derivative of extensive property in the CV, and we had just derived the expression for B in CV as this quantity, all right. So, we say that this whole thing, all right, this whole expression we derived and we said this is equation number 4. So, that was the first component, which is the time rate of change of extensive property stored within the control volume, that is component number 1. In the component 2 of the Reynolds transport theorem, we have two terms, one is at the outflow region and other is at the inflow region. What we did is we look at the magnified or we took the magnified view or illustration of what is happening at the outflow region. So, we looked at this region which we have drawn here, all right, in which in the outflow region we took a very small elemental tube of volume dV and cross sectional area dA, and wherein we defined various terms where dA is the cross sectional area, the volume is dV, and theta is the angle, this one, between the velocity vector and the normal vector normal to the dA, right. Using this we get different terms, that is length of this tube is V times delta T, and dV was defined as area multiplied by the length of that particular element. So, it will come out to be delta L cos theta dA. Then what we did is we tried to write the expression for the total amount of B in region 3. Why? Because region 3 is the outflow region and we want to write down the expression across the whole cross sectional area dA at the outflow region. Okay. This we said under the limits of your B3 at time t plus delta t, all right, is nothing but under the limits of this expression which we derived here, all right. And then we use the simple definition of your, this is how the velocity is defined. This is the dot product of two vectors v and dA, that is v dot dA. If we put all these things in this expression, and this came out to be the total integral or double integral over the whole cross sectional area or the control surface times beta rho v dot dA. Then what we said is we can carry out a similar analysis at the inflow region, and we will come up with a similar equation, which was this. This was the similar analysis for the inflow region. This is what we had just derived, okay, and this was the component 1, and this is the left hand side, all right. So, if we combine the last two terms into a single term and we say that across the whole cross sectional area, what is the quantity beta rho v dot dA flowing across the whole control surface, all right. So, this is your final expression for the Reynolds transport theorem, okay, which consists of these two components. First one is the time rate of change of extensive property stored within the control volume, and the second one is the extensive property flowing across the control surface. Then we looked at some simple concepts of various possibilities of value of theta, in which we said that at the inflow region your theta will be in this range. That is why the inflow, if we take negative, we do not have to worry about the dot product. At the outflow region your theta will always be less than 90 degrees, that is why cos theta is positive. So, we take the outflow flux as always positive, and across the boundaries there is no flow. So, theta is 90 degree and v dot dA will always be 0. Okay. So, this is what we had done in the last class, all right, the derivation of the Reynolds transport theorem. What we would like to do today is to take this concept of the Reynolds transport theorem and look at the continuity equation, all right. So, first we will start with the continuity equation and then we will take up the momentum and energy equation also, how we can derive or how we can deduce these basic laws of physics which we apply routinely to all our fluid flow problems using the Reynolds transport theorem. First we look at the continuity equation. The continuity equation can be written or can be of three types. Okay. It could be for the fluid volume, it could be for the flow cross section, or for a point within the flow or flow regime. Okay. I am sure you have seen some of the examples of these continuity equations. Okay. Can you think of an example of continuity equation for a point within the flow region? I am sure you may have done the problems on the pipe flow analysis or the water distribution system design, in which what we do at each junction is all the flow coming into the junction is equal to all of the flow going out of that junction, all right. So, that is the example of a continuity equation at a point, that is this one. Okay. And flow across a cross section, we are all familiar, the amount of or the volumetric flow rate flowing across a particular cross section is equal to the same at the next cross section if the flow is steady. However, what we are going to do is we will look at the integral continuity equation in the fluid volume, all right. So, let us look at this. integral equation of continuity. Okay. As we know, what is a continuity equation? It is nothing but the expression for or representation of law of conservation of mass. Okay. So, the extensive property in our this Reynolds transport theorem will be the mass of the fluid. Okay. As we said that we derived this general control volume theorem or the Reynolds transport theorem for any general extensive property, and when we are trying to derive the continuity equation is written for mass. So, we will take capital B is equal to the mass of the fluid that is flowing. So, mass is the extensive property. Okay. What will be beta then? I would like you to think about it for a second and convince yourself what would it be. What is the relation between beta and B, that is intensive and extensive property? It is the dB over dm. All right. So, what will be the dm over dm? It will be nothing but 1. Okay. So, for the law of conservation mass, your extensive property is the mass and intensive property will be 1, constant always. Okay. Also, as per the law of conservation of mass, what do we have? It states that the matter cannot be created or destroyed. All right, it has to be conserved. Right. So, what does that mean in terms of dB over dt? That is dm over dt. That has to be equal to what? If the mass has to be conserved over time, 0. Okay. So, dB by dt will be 0. So, this is the left hand side of your Reynolds transport theorem. Okay. So, we substitute all these things, substituting these concepts in your Reynolds transport theorem. Okay. What we will get is the left hand side is 0 and then the first term is d over dt of your triple integral over the control volume of your beta rho dV, and beta is 1. So, you have 1 rho dV plus the extensive property, that is mass flowing across the control surface, that is double integral over the cross section or the control surface. Beta is 1 rho V dot dA is equal to 0. Now, say that your density of the fluid when the fluid flow is taking place is constant. If we make that assumption, that is to say we are saying that the flow is incompressible, that is there are no density differences during the flow motion. So, we can say that under the assumption of incompressible flow. What will happen is rho will drop out of this equation because rho becomes a constant and we can take it out of the integral. Okay. So, what we have then is d over dt of triple integral over the whole control volume, rho is gone. So, you have dV plus over the cross section or control surface, you have V dot dA is equal to 0. Okay. And I am going to name this or number this equation as 10. Now, what we do is we look at these two expressions individually. All right. just think about physically what is this quantity representing. That is to say, or let us leave the d by dt aside for a second and try to think what is Cv or the integral of the whole volume within the control volume is what? If you put rho here, it is basically the total mass which is there in the control volume, all right, but rho is out, so it is the total volume. So, what we say is then this is the volume of fluid stored within the Cv, okay, and let us represent that total volume that is stored within the control volume as capital S. S is the storage, let us say, all right. Then what is this whole quantity? This is nothing but ds over dt. Is this clear? Okay. Try to convince yourself, all right. The first quantity or the first expression in equation 10 is nothing but ds over dt. Okay. Now, let us look at the second quantity. Okay. What is this represent or what does this represent physically? Physically, it represents the extensive property flowing across the control surface, and the extensive property is mass, all right, and because we have taken the rho out, so we have the volumetric flux flowing across the control surface, all right. So, let us say that your this second quantity represents the volumetric flux across the control surface, all right. This we say is equal to, we can break it up into two parts. Let us say at the outlet region or the outflow region, what is V dot dA, and at the inflow region, what is V dot dA, okay. And this we say is equal to, what is the flow at the outlet region, let us say it is Q, all right, volumetric flow rate, and this is I or the inflow in the volumetric flow units, okay. And let us say this is your equation number, if this was 11, I say this is 12, all right. So, we put 11 and 12 into 10. So, what we will get is ds over dt plus your qt minus it, all right. Remember what is qt minus it? It is the net outflow, okay, and all of this should be equal to what? Should be equal to 0, all right, or we take the inflow and outflow quantities on the other side. So, you have this is equal to I minus qt. Does this sound familiar? I am sure it does. Okay. This is nothing but your famous continuity equation for the unsteady flow, all right. So, this is the integral or volumetric continuity equation for unsteady flow. Okay. What happens when the flow is steady? There will be no change in storage, all right, or any quantity which depends on time will be constant, or the changes with respect to time will be 0. So, for the steady case or for steady state case, your ds by dt term will be 0. That would mean your it is equal to qt, okay. Inflow is equal to outflow, okay. So, if you think of an example of a channel flow in which the same amount of flow is passing through a particular reach of a channel, then we know that the discharge is constant, okay. Same discharge is flowing. So, inflow is equal to outflow within any reach, okay. And I will number this equation as let us say 13. and this is for the steady flow. Okay. So, moving further, I would like to just caution you one important point about the use of this continuity equation. Okay. The continuity equation which we have just written above applies to a single phase flow. That is, the fluid is in a single phase, either liquid or gas. All right. However, if you have the multi-phase flow, that is, if you have a physical process in which the fluid is occurring in more than one phases, that is, there is gaseous phase involved and there is liquid phase involved, or any other solid phase may also be involved. Okay. So, if that is the case, then we need to write the continuity equation for each phase. Okay. For example, evaporation. When the water is evaporating from the water bodies, let us say rivers and lakes and dams and reservoirs. All right. So, you have a multi-phase flow kind of situation there. There is condensation taking place, there is evaporation taking place, and the net escape of water is called the evaporation. Okay. So, in that case, we need to write the continuity equation for liquid phase and vapor phase separately, need to be written. Okay. We will come back to this concept little later in this course when we will look at the process of evaporation. Okay. The other thing I would like to mention that for a closed system, all right, we should have the integral of the quantity of your inflow should be equal to the total quantity of your outflow. All right. Or in other words, if the total inflow volume is equal to the total outflow volume, then it is a closed system. Moving further, the next thing we are going to look at is what is called the discrete time continuity. As we know, most of the hydrological data are continuous in nature, or most of the hydrologic variables, I should say, are continuous in nature. For example, rainfall or flow in a river. The stream flow in a river is changing continuously with respect to time. All right. However, when we measure these variables, for example, when we measure the flow in a river, all right, the data which we have available are at discrete time steps. For example, we will probably measure them on an hourly basis or on a daily basis. Similarly, for the rainfall, rainfall also we will measure at discrete time steps. Okay. So, all the equations which we have written, we need to write them at discrete time steps. That is why understanding the discrete time continuity becomes important. Okay. So, what we do is we write the CE at discrete time steps, and that is called the discrete time continuity. Okay. So, if we look at the concept, this is your time domain, and time may be in hours or days or any suitable units, and the quantities you have is either S or I or Q. All right. It may be varying. I do not want to draw the graph. The important thing here is that we discretize the time domain like this, wherein we say this is 1, 2, 3 and so on. Then let us say this is your jth time interval and so on. Okay. And each of these interval, let us say, is delta t, okay, which can be either constant or variable. Okay. But in most cases we keep it as constant. okay, for the ease in implementation. For example, every day we measure the rainfall, all right. Okay, so if we apply the our continuity equation which we have just derived, ds by dt is equal to it minus qt, okay, or we say your ds is it dt minus q dt. Okay. Now, what I will do is I will integrate this equation on both sides. That is to say, if I integrate this under the limits, the storage at, let us say, being general at Sj minus 1, we are writing this at the jth time interval. So, Sj minus 1 to Sj will be equal to your integral of your it dt, where the variable is dt and the time is varying during that jth interval from j minus 1 delta t to j delta t. Okay. Similarly, integral of your qt dt of j minus 1 delta t to j delta t. Okay. Or we say that this is, after you integrate, it will be Sj minus Sj minus 1, okay, and I represent this as, let us say, Ij minus Qj, all right. Whereas what is Ij? Ij is this whole quantity. This is Ij, and this whole quantity is Qj. Okay. And how I define them is basically your Ij is the volume of inflow during time interval delta t, and similarly your Qj is the volume of outflow during time interval delta t. Okay. So, in other words, I can write the equation delta Sj is equal to Ij minus Qj, which is nothing but Sj minus Sj minus 1, or you can write the expression for Sj as Sj minus 1 plus Ij minus Qj. Okay. And let us say I am going to name this as equation number 16. So, this is my discrete time continuity equation, at least in the partial sense. Now, what we do is we can apply this equation at each time interval, so that we will have a general expression, all right. Each time interval means, let us say, we will apply this at j is equal to 1, j is equal to 2, j is equal to 3, and so on, if we have capital N number of time intervals. Okay. So, if we do that at j is equal to 1, then we will have S0, all right, and S0 is something, the initial condition or the initial storage. So, if we say that the initially the storage is, let us say, S0, then what will be S1 as per equation number 16? It will be nothing but S0 plus j is 1. So, I1 minus Q1. Okay. Now, we write the same equation at, let us say this was at j is equal to 1. Now, we write this at j is equal to 2. That will be S2 is equal to S1 plus what? I2 minus Q2. Now, what is S1? You put S1 from this equation into this. So, it would be nothing but S0 plus I1 minus Q1 plus I2 minus Q2. Okay. Similarly, for j is equal to 3, you will have S3 is equal to S2 plus I3 minus Q3, and the value of S2 we put from here into this, and that will give you this as S0 plus I1 minus Q1 plus I2 minus Q2 plus I3 minus Q3. So, you see that there is a pattern here, all right, and once we recognize a pattern, we can just capture it. So, you say that in general at any jth time step, your Sj is going to be equal to S0 plus summation, where summation will be varying from 1 to j, let us say this is I, it will be II minus Qi. Okay. Okay. So, this summation is I actually. Let me write it again. Okay. I am going to write it again. So, it will be summation I running from 1 to j. Okay. And let us say this is your equation number 17, which is called the discrete time continuity. Or in other words, it is the continuity equation in discrete time domain, which we can use to analyze the data which are measured at discrete time interval. All right. So, let us move ahead and look at the different ways of data representation methods. There are various variables which are measured over time, but even at the discrete time intervals at which they are measured, we represent or store the data, or the method of representation can be different. Okay. So, there are basically two different types of methods or two different ways of data representation. Okay. These are called sample data representation or function, and the other one is the pulse data representation or function. In the sample data representation, what we do is we just simply measure the data at the end of a time interval period. Okay. And we say that the value of the physical variable during a time interval is its value at the end of the time interval. Okay. And in the pulse data representation, we say that the cumulative value of a particular variable which we measure, we say represents the total value for that time interval, which will be represented by the area under the curve for that time interval. So, let us look at these definitions and graphically how we represent it. So, here we say that the value of a function, let us say the function is q, in the jth time interval, and we will say that it is qj, is simply given by the instantaneous value of your qt, that function, at time j delta t, that is at the end of the time interval. Okay. So, if you look at it graphically, what does it mean? So, if you have a stream flow which looks like this, and then we have discretized the time domain. Okay. So, this is your first interval, second interval, and so on, and the jth interval. So, during the jth interval, this one, what we are saying is that we take the value at the end of the time interval. Similarly, j minus 1 is this one is this, and so on. Okay. So, we say that q at j is nothing but the value of q at time j delta t. Okay. So, this is called the sample data representation. Okay. Let us look at the second one. Let me draw a line here. In this one, the value of discrete time function qj is given by the area under the continuous curve. Okay. That is to say, your qj is equal to the area under the curve, and that curve is that function is qt, and j is the time interval. So, we run the integration between j minus 1 delta t and j delta t. Okay. If you want to look at it graphically, how we represent this as, let us say it is in the form of bar chart. This is 1, 2, this is your jth time interval, and so on. So, we take the area under the curve. So, this represents your qj for the pulse data function. Okay. The x axis is time and y axis is qj. So, you see that in this first one, that is the sample data function, this q is normally in L cubed by t units. Okay. And in the second case, this could be in either L cubed unit or L unit or L cubed by t unit, depends upon how we are defining our particular variable. Okay. Can you think of an example of these two data representation, sample data representation and the pulse data representation? Yes, the sample data representation is the instantaneous value, and that is how we represent the stream flow. And for the pulse, as you can see from this bar chart, it is the rainfall in the form of rainfall intensity per unit time we define. Okay, so we looked at the derivation of the continuity equation from the Reynolds transport theorem. Okay, and then we looked at the volumetric form of the continuity equation or the integral continuity equation, and then we also looked at the continuity equation at the discrete time step. Okay. So, now what we will do is we will move on to the momentum equation or derivation of momentum equation from our knowledge of this Reynolds transport theorem. Okay. So, when we are writing the momentum equation, what is the extensive property B? Obviously, it has to be the momentum or the fluid momentum of fluid. Okay. Or your B is equal to, what is the momentum? Mass times velocity. That is how the momentum is defined. Now, can you tell me what will be the intensive property beta? This is defined as your dB over dm. So, if you take the derivative of this quantity m times v with respect to m, what you will have is the velocity v. So, for the momentum as the extensive property, velocity is the intensive property. Okay. So, keep that in mind. Now what we do is we write our Reynolds transport theorem. Okay, you have to remember this equation by your heart. It's like Manning's equation. You cannot never forget. All right. So the Reynolds transport theorem you should understand in such a way that it just comes out. So dB by dt is your d over dt triple integral beta rho dv plus double integral control surface beta rho v dot dA. Okay. Remember, in the continuity equation we said that dB by dt is equal to 0. What was that? That was the law of conservation of mass. So we write the left hand side using an external knowledge. Similarly, what is the d over dt of momentum? All right. What is the time rate of change of momentum? You have to go back to your knowledge of physics, 12th standard, or maybe your first few years of engineering degree, and tell me what is the basic law that gives you the time rate of change of momentum. Okay. Yes, it's given by the second law of, or second Newton's law, or the Newton's second law of motion. And as per that, what is the time rate of change of momentum? It is nothing but the net force acting on the body. Okay. Earlier you have done in terms of the body, and now it is in terms of the control volume, okay, on the flowing fluid. So this is, you can write your dB over dt is equal to the net force summation F, which is acting on the fluid control volume. Okay. All right. So with this knowledge, what we will do is we will put all these equations in our Reynolds transport theorem. Okay. So that you will have summation F, that is the left hand side, is equal to d over dt of triple integral beta is v, we have seen that, rho dv plus double integral over the control surface v rho v dot dA. So this is your most general momentum equation for any kind of fluid flow problem. All right. And this we will say is the integral momentum equation for unsteady, where things are varying as a function of time, non-uniform flow, non-uniform flow. All right. What is a non-uniform flow or a uniform flow? Do you understand the difference between uniform flow and non-uniform flow? Yes, a uniform flow is something in which things are not varying with respect to space, and in a non-uniform flow the velocity and other parameters will be varying with respect to space. Okay. So let us move on further, and if we want to write out this equation for steady non-uniform flow, if you want to write out the momentum equation for steady flow, but it may be non-uniform, what will happen is the things are not changing as a function of time. So the first term on the right hand side will vanish. Okay. So we can write that the net force acting, the first term is 0, so it is only the second term, v rho v dot dA. Okay. So this is for the steady non-uniform flow. How about for steady and When the flow is uniform, what does it mean? It means that the velocity and other hydraulic parameters are not changing with respect to space. Okay. So, if the things are not changing with respect to space, and in this term we are taking the integral with respect to the area, all right. If with respect to different areas or different points in your control volume, if the velocity is constant, then this whole quantity will also be equal to 0. If you take the v dot dA term, because the velocity is not changing, then this will be 0 because of the uniform flow. So, for this momentum equation then will become summation f is equal to 0. Okay. So, this is the momentum equation for the steady uniform flow. Okay. Now, what we will do next is we will try to apply some of this different types of momentum equations to some flow situations. Okay. I would like to take up a example problem, and this kind of example problems I am sure you may have done earlier in your classes. Okay. So, this is the example of a 60-degree elbow. In the pipe distribution network system, as you know, there are many kinds of pipe fittings. All right, there will be T junctions, there will be elbows, there will be 90-degree elbows and valves and so on. Okay. So, what we are doing here is, let us say we have a situation so this is a pipe fitting, okay, wherein all the data are given. This is a 60-degree means this angle theta is 60 degrees. All right. This is your x direction, this is your y direction. The velocity of flow or the direction is in this horizontal direction. Let us say this is v1 here, and the water comes out with the velocity v2 here, and the cross sectional area of this elbow here is a1, and let me define it that this is cross section 1, this is cross section 2, and this is a2. So, flow is taking place under steady state condition. So, you have a case in which water is flowing through this 60-degree elbow, all right, constant quantity Q is flowing under steady state condition. So, things are not changing or flow is not changing with respect to time. Okay. And the data that are given are Q is equal to 1 meter cube per second, which is steady state. Other thing that is given to you is the P1 G, which is the pressure force or the pressure that is acting at cross section 1. All right, there will be some pressure acting, is 0.1 million pascals. Okay. Also given to you is the pressure at the cross section 2. G is the gauge pressure that is above atmospheric, that is I am sure all of you understand this terminology. So, this is 0.09 million pascals. Okay. So, these two pressures are given. Also given to you is, let us say, the area of cross section at the inflow region is 0.1 square meters, or you may be given the pipe diameter to at the inflow region where this elbow is being attached. So, you can find out that area A1, and similarly your A2 is given as 0.07 square meters. Okay. What you have to find is the resultant force on the elbow is equal to what, and other data that is given to you is neglect the weight of water. Okay. So, these are the data that is given to us. The flow is given, the cross sectional areas are given, the pressures are given at the inflow and outflow region. Neglect the weight and find out how much force will be acting on this elbow. Okay. All this analysis is important to design all these fittings, so that they are able to withstand the force that will be acting on them in the real life situation. So, what I have drawn here is that this is the control volume. So, what we will do is we will apply our steady state momentum equation to this control volume and find out what are the forces which will be acting on this in the x and y directions. Remember, the momentum is a vector quantity. So, we will write the x direction momentum and y direction momentum equation. Okay. Let us do that. So, for the solution, we say consider the CV shown. Okay. So, in fact, what we will do is we will solve this equation by using continuity equation and momentum equation. All right. So, it will be a combination of these two things. All right. And once we apply this, we will be able to calculate the forces. Okay. I think what I would like to do is I would like you to think about this problem, and in the next class you come back and look at how we are going to solve this particular problem. Okay. So, at these two cross sections we have seen the continuity equation, we have seen the momentum equation. You apply this at these two cross sections or this whole control volume and see if you can come up with the answer of what is the force that will be acting on this elbow. We will look at the solution in the next lecture.